Here we have the function f of x is 1 over x, and I've already split the page in half because we're finding lots of information. So again, starting with the first derivative, that would be critical numbers, whatever makes the first derivative 0 or undefined. We would get relative max and min if we had some sign change on our sign charts that are telling us increasing and decreasing. Whereas second derivative world would be giving us inflection points, what makes the second derivative 0 or undefined, and has that concavity change. So concave up and concave down are also second derivative. So starting with the first derivative of this, well, I have to rewrite this function, first of all. I don't want to have to use a quotient rule, and I don't have to unless I have x's in both the top and the bottom. So I'm just going to rewrite this so that I don't have a fraction anymore. This is x to the negative 1. Negative because the power is in the denominator. And now I can take the first derivative of it and set it equal to 0. So I'm going to bring down the power negative 1. X to the negative 1 minus 1 is negative 2. And I'm going to set that equal to 0. And in order to solve this, I need to put that negative exponent down where it belongs. So the first derivative is really negative 1 divided by x squared. Putting that in the denominator. So we want to see what makes the first derivative 0. So one thing we can do is set the top to be 0 and then set the bottom to be 0. So we'd have negative 1 equals 0, and we'd have x squared equals 0. Well, negative 1 is always negative 1, so we can't make that 0, but if we want something squared to be 0, we could take the square root of both sides to solve this, by the way, if you need to. Or you may know that the only number that squares to be 0 is 0. So there is our critical number maybe. Remember, critical number just has to make the derivative 0 or undefined. This makes f prime undefined, which is great, but remember when it makes it undefined, it may not go into the original function. So if it's not a number that goes into the original function, we don't get to call it a critical number. So let's see if we can do that. So let's plug in 0 into the original function. F of 0 would be 1 over 0, which is undefined. It makes us divide by 0. It's a number divided by 0, so we know it's actually a vertical asymptote. So this is no critical numbers for this one. There are none. This is going to be a vertical asymptote. It's not a number that's on the graph, so it's not going to be called a critical number. That was the one picky thing about critical numbers, is they have to go into the original function to be called a critical number. They don't have to have a change in the sign chart, but they do have to go into the original, and the only time we're concerned that it may not go into the original is if it makes us undefined in the derivative. Then we know we have to check it. So this is not like the cube root of x example where our possible critical number makes us undefined in the derivative but can go into the original. This one cannot go into the original. So we simply do not call it a critical number, but we're going to use it the same exact way that we would a critical number on our sign chart. This makes f prime undefined. We're still going to check numbers to the left and to the right because this is the only place where we might have a switch in increasing and decreasing, or relative max and min. But we already kind of know this is not going to be a relative max or min because it is a vertical asymptote. So we can at least look for a change in increasing and decreasing. I'm going to test any number to the left of 0. So maybe negative 1. And I'm going to plug it into the derivative. The top of the derivative is always negative 1. So that's always negative. And then the bottom, negative 1 squared is going to be positive. So I'm going to have a negative divided by a positive, which means I'm going to be decreasing to start. And then after 0, I can plug in anything. Maybe I'll plug in positive 1. The numerator of the derivative is always negative. And then 1 squared, 1 to any power, always just stays 1. So it's positive. So we have a negative divided by a positive again. We have 2 decreasing intervals. So definitely no relative max or relative min point. There's no sign change on the sign chart, and we also know that this is where there's a vertical asymptote on the graph. So no relative max, no relative min. For increasing, there is also no interval of increasing. And for decreasing, we're decreasing before our critical number that didn't end up turning out to be a critical number and after. So before 0 and after 0, still a special number, just not called a critical number if it's not in the domain of the original function. So we would not say negative infinity to positive infinity because at 0, the derivative is undefined. It's not decreasing there. It's undefined. All right, so we're going to keep working with these. Let's look at the second derivative now. Kind of tough interpretations when we have a special number that's not on the domain or within the domain of the original function. So we're going to take the second derivative. I'm going to look at this form here. We have -1, and we're going to bring down the power of -2, which is going to make it positive 2. -1 times -2 is positive 2. And then we have x to the -2 minus 1 is -3. We're going to set that equal to 0. To solve this, we're going to put negative exponents where they belong, and then solve it like a fraction. So we want to see what makes the top 0 and what makes the bottom 0. So looking at this, we want to make the top 0 and we want to make the bottom 0. So nothing makes 2 equal 0. 2 is always 2. And then we want to think of a number that we could cube it. We could multiply it by itself 3 times and get 0 out. So that would be 0 cubed, because 0 times 0 times 0 is going to give us 0. So there's our special number. It's our possible inflection point. So we're going to use that on our sign chart here. We'll put 0. And we can test any number to the left and to the right. So to the left, maybe I'll just test -1 again. The top is always positive 2. So the top is positive. And the bottom is going to be -1 cubed. So -1 times -1 is going to be positive 1, but then times a third -1 is going to make it negative, which you could check in your calculator. -1 cubed is negative. So we have a positive divided by a negative, which means the second derivative is negative now. So that means that it is concave down. So we're concave down. And then after 0, we could plug in positive 1. And into our derivative, our second derivative, so we'd have a positive 2 as our numerator, and then 1 cubed is just going to stay 1. So we'd have a positive divided by a positive is a positive. So we'd have concave up. So it looks like we should have a point of inflection, right? We have that switch in concavity. But we remember if we try to plug in this point, 0, into the original function to find the y value, we're going to get 1 divided by 0. So it's not a point on the graph. It is a vertical asymptote. There is no point of inflection. It met everything that it needed to. It made the second derivative 0 or undefined, which was great. It had a change in concavity, which was great. But one stipulation is if it's not a point on the graph, then it's not a point of inflection. So lastly, concave up and concave down. We would say concave up from 0 to infinity, and concave down from -infinity to 0. So we have a pretty good idea of what this all looks like, and we can try to sketch a picture of this. I'm going to move this back down where it was. You'll have more space on your notes packet. I moved mine up so you could see it all in the same picture. So let's do a little sketch of this because the next section we're going into is curve sketching. So we want to be able to sketch what this curve would look like. So sketching this, we have a vertical asymptote to put on here first. We have a vertical asymptote at 0. So we're not going to touch this line here. We can't have a y value here because we can't plug it into the original. And then before 0, we're just going to sketch. We don't know exactly where this looks. We could plug in and find some points if we wanted a better idea. But we just want to draw something that is decreasing and concave down, because that's what's happening before 0. We are decreasing and concave down. So let's look at this concave down. It could be a full upside down U. it could be just the left side, or it could be just the right side. We want to pick the picture that's always decreasing. So this first piece is increasing. It would have a 0 first derivative, then it'd be decreasing. The first derivative on this is always rising, so this one's always increasing, and this one's always decreasing. So this is the first piece we want to draw. This is decreasing and concave down. It might not look exactly like this. We'd have to graph some points to figure out where that shape should be. But there's decreasing and concave down. The next interval after 0 is supposed to be decreasing but concave up to match this sign chart. So we want to find something decreasing but concave up. So we're going to draw our 3 U's, but for concave up this time. So concave up could be a full U. It could be just the left side of the U, or it could be just the right side of the U. We want to figure out which one's always decreasing to match that first sign chart. So this one's decreasing, has a 0 derivative at a soft peak, then it's increasing. This one's always decreasing, and this one's always rising left to right. So that one's always increasing. So we want to draw this picture here on our graph. So we want to be oriented upward, but decreasing. So we want to look like the left part of a U. So there's a random sketch of what this could look like, just to get us ready for some curve sketching, but a more unique function because our critical number happens at a vertical asymptote, so we don't get to call it a critical number. And then same thing with our inflection point, also happens at a vertical asymptote, so we don't get to call it an inflection point.